Lab11, Galactic, redshift, and cosmology. So this is basically the relationship between velocity and distance. First time Hubble tried to measure galactic velocities. So basically we start from our Milky Way and looking at different galaxies at different distances. And what we see is they all are moving away from us. So if we use their spectrum, we can use redshift and blue shift. And when we see a redshift, it means they are moving away. So this is redshift for one galaxy. Another galaxy is a little further away. This is redshift for the second one and the last one. And further they are, redshift is larger. You see, this arrow represents the redshift. This is happening for all galaxies, and it looks like they are all moving away from us. So let's say we use v for velocity, and we have their distance, and we plot velocity versus distance. We start from Milky Way. Milky Way is our reference, so it's 0 and 0. This is 1 point. We put another galaxy. It's closer. Recession velocity is smaller. Another galaxy, it's further. Recession velocity is bigger. So we have these points. And it looks like it's a line. So it means velocity is proportional to distance. Further they are, faster they move away. So we can use this proportionality. So velocity is proportional to distance, but we can go further. We can add a constant to find the relationship between velocity and distance. So velocity is equal to h times d. This is Hubble's law. For distance, in this case, we use megaparsec. That's a huge distance. For velocity, we use kilometers per second. And this formula is called Hubble's law. Basically, velocity is proportional to distance is Hubble's law. We need a constant. This constant is h, and it's called Hubble's constant. Sometimes we put a small circle just to make sure this constant is for this time. But all are the same, h or h naught. And for Hubble's constant, we have kilometers per second per megaparsec. If we have this plot, we can use the line to find this constant. Basically, h is the slope. If we have this slope, we can calculate Hubble's constant. So h is the slope, and we can use 2 points to calculate the slope. So easiest case is to use 0 and 0 and use a second point. And for the slope, if you remember, is the difference in y divided by difference in x. So v minus 0, d minus 0, it will be v divided by d. Okay, let's see how it works in this lab. In your manual, there's a table, and in this table we have few galaxies. So this is a small table for few galaxies. And we have their distance and their velocities or recession velocities. And if we put all distances and velocities in one plot, we can see that linear relationship. So this is the plot for a linear relationship. Velocity is proportional to distance. You can see not all points are exactly in line. There are small errors, but it's almost a line. And you can see if we fit a line, v is equal a number times distance. And this number is h. Okay, how to do this assignment? For your assignment, let's say we have this plot, and you can use that plot to find the true h, or Hubble's constant. The next step is a table like this. We have galaxies and you have their redshift. Just measure their redshift in millimeters. So this is just the ruler. Use a ruler or a scale and measure the length of this arrow. It's very small for the first case. Then we can calculate delta lambda, or change in redshift, or wavelengths. Delta lambda is a scale multiplied by delta r. You have this scale, it's a constant number for all cases. It's 21.7 times delta r. So take that number you measured in millimeters, then multiply by 21.7, and you get your delta lambda in angstrom. Now you have delta lambda, and you can use Doppler shift for velocity. V is equal to c times delta lambda divided by lambda. In this case, lambda is a constant number, 4,000 angstrom. C is the speed of light. It's 300,000 kilometers per second. And delta lambda is in your table. C and lambda are constant numbers for all cases, so you can just do the math and get 75 times delta lambda. So it means you can do it simpler. Take your delta lambda and multiply by 75, then you get velocities. Now let's do h. This is not a good way and the best way to find h, but we are just examining this idea. So v is equal h times d. If you play with this formula, h is v divided by d. Basically, we are using single point. And for units, we have kilometers per second per megaparsec. So for the next column, for h, use v divided by d. Distance is given, you have that number. And finally, for the error, just take h, whatever you have for h, you have different numbers for different galaxies, and you have one true value from the first plot. Just subtract and find this difference and use positive numbers. This is the error. So it looks like this. You're multiplying one column by number, then you move, you get h, and finally you subtract different h from true value to get the error. Okay, moving to the next part. You can use the best h you have, the minimum error, and use this h for the rest of the slab. There are a few questions you have to calculate distance. It's the same formula, just play with it. V is equal h times d, so distance is equal to v divided by h. And distance is in megaparsec. Sometimes you need v, sometimes you need distance. But h is a number you got from your best value in the table. There are questions for the age of the universe. So there are two questions. First question, just follow instructions. Another question is using Hubble's law. So basically, time is d divided by v. So we can put hd, and if we simplify, T is equal to 1 over h. So h is 1 over Hubble's constant. That's very cool. But problem is this is in very strange unit. So you have to convert from one unit to another unit. And there are numbers in your manual. But make it simpler. So this is how to convert. You have two numbers. Divide these two numbers and find the value. This is your conversion number. Then take that number, divide by h. That will give you the age of the universe in years.